Hi, everyone. Here's a key issue with polls, the sampling rule for treating dependent events as independent. When we conduct polls, we sample without replacement so that the same person is not contacted twice. We don't want to bug that person. So technically, the selections are dependent. Now, sometimes to simplify our calculations, we can treat dependent events as independent, and our results will basically be reasonably accurate. We can do this when we take relatively small samples from large populations. Then we can practically assume that we are sampling with replacement, and we can ignore the unlikely possibility of the same item or person being selected twice. So that basically we can treat dependent events as independent, and we can assume independence. We assume independence for practical purposes. And we'd like that because remember, the calculations were a lot easier, like they might involve an exponent, for example, if we're dealing with independence. With dependence, those calculations tend to be more awkward and complicated, like this countdown stuff we dealt with over here. Independence calculations tend to be easier. So under what circumstances can we apply the sampling rule? Well, when the population is big enough, for our class, let's say at least 1,000, let's say, then even if you're drawing without replacement, you're promising not to call the same person twice. If your sample size is no more than 5% of the population size, then that means that you're drawing a relatively small sample from a large population. And we can assume independence. We can practically treat the selections as independent. By the way, the 1,000 is just a number I picked for our class. Here's an example. Let's say that we look at the popular vote for president in 2000. George W. Bush, the electoral vote winner, won 47.8%, although Al Gore won the popular vote. He won 48.4% of the popular vote. Over 105 million voters voted in that election. That's a lot. I think that's pretty big for Big N. That's a lot. Of those, 3, that's relatively small, way less than 5%. Of those, 3 are randomly selected without replacement. I mean, the probability of calling the same person twice anyway is minute. Find the probability that all 3 selected voters voted for Bush in 2000. Now, there's no point in doing countdowns. I mean, these percents are rounded off anyway, so there's no point in doing the whole countdown nonsense. We don't have to worry about the 105 million. That's a lot of voters. Okay, find the probability all 3 voted for Bush. So, again, we're sampling no more than 5% of a huge population. We're going to apply the sampling rule, and we're going to practically assume that the selections are independent, even though they're technically not. Since Bush won 47.8% of the vote, remember, we like to convert to decimal when doing calculations. The probability that a randomly selected voter voted for Bush is 47.8%, or as a decimal, 0.478. So what's the probability that 3 random voters voted for Bush, assuming independence? I'll give you a hint. Remember this calculation up here, the ace-king-king problem where we assumed independence. Again, use decimals, not percents. Find the probability that all 3 selected voters voted for Bush. It's the probability the first voter voted for Bush times the probability the second voted for Bush times the probability the third voted for Bush. Each of these probabilities is about 0.478, or 0.478 cubed to the third. That turns out to be about 0.109, or 10.9%. Now, let me ask this question. If a news network says that it randomly picked 3 voters from the 2000 election, and all 3 of them said they voted for Bush, there's a 10.9% chance of that happening, just by chance, assuming that the process was appropriate and we assumed independence. But if a news network claimed that it really was a random selection, what might you ask? Were they really being truthful? Is this too low for us to assume that the network was playing fair? and actually selecting them randomly based on a simple random sample? If this probability is too low, then we might really question that network's honesty, at least in this regard. That's an issue for inference later on in the course.